I hope the food was good. I know I ate too much of it. It was that delicious. So while we digest that excellent meal, I'd like to introduce you to a colleague of mine who I have the privilege and pleasure of working with, Richard Sheehan from Facebook.
Thank you. So today I'm going to talk about network monitoring at massive scale, or at Facebook scale. So for people who don't know me, I've been in this industry for a long time, but I worked for Amazon for 10 years and they don't like you to talk about anything they do. But I can say that I'd worked there for 10 full years and I didn't cry once, which apparently is very rare. So, actually, well, it means one of two things, right? It means either it's not that bad a place to work or an amazing hard ass. So I know which I'd like to believe and I know which is the truth. So I'll let you guess which one is which. So we're going to talk about the basics of fault detection inside a network and how people fix these broken networks. So usually when most companies start out, they're reasonably small scale and they have no network monitoring. They just plug a bunch of stuff together and they hope that it works. And what happens is, very quickly people start to tell you when the network is broken. But then what happens really quickly is that people start to tell you when they think the network is broken, which means anytime there's any kind of problem, people say, hey, we're pretty sure the network is broken. And as a network engineer, or as a production engineer, or an SRE, you end up having to investigate absolutely everything. And the problem is, because you don't know if there's a problem or not, you have no idea. And this brings me to the first SRE principle, which I think most of us are familiar with. Your customers should never tell you about your problems, you should already know. So if a customer tells you, you've got two issues. You've got the issue they've reported to you, and you've got the bigger issue of you had no idea your shit was broken in the first place. So how do human beings debug network problems? Well, firstly, they use the standard tools, ping, hping, mtr. They try and find out where the broken link, broken device, or broken path is, and they fix it. But this doesn't scale. So what most people do pretty quickly is when they do this manually for a while, it's like, you know what helps? Graphs. Because a lot of network outages boil down to two things. You run out of capacity, or you have a bad device that's dropping packets. So you have some traffic graphs, you have some error graphs. And then maybe you graduate on a massive big knock like this and say, hey, we can look at screens all day long. But that's actually pretty lame too. So, Facebook scale, how we deal with our much larger than normal networks. So I have to introduce how our networks work. So we have two fundamental networks at Facebook. The first is our data center network. So these networks are big. This is where we have the vast majority of our devices. They're multi-stage CLO or CLOS topologies, depending on how you want to pronounce it. They're characterized by lots of devices, lots of links. They run BGP only. They run IPv6 and IPv4. We have IPv6 everywhere in our data center networks, which is actually a pretty cool thing that not many people do. And there's a huge ECMP fan out. But to explain what that means, I'm going to define ECMP. ECMP is equal cost multipath. To explain, in this diagram, we have two hosts, host 1 and host 2. They want to talk to each other. So host 1 wants to talk to host 2, sends a packet to his rack switch. The rack switch then has a choice. He's got two paths that are going to take him closer to this other device. So what he does is, back to TCP/IP illustrated, he looks at the TCP packet and he says, okay, there's 5 fields in here that I'm going to perform a hash on. The protocol, source address, destination address, source port, and destination port. So he creates a hash of that and then decides based on the hash which link he's going to send it on. So in this case, send it to the right. Again, same process, next router makes exactly the same decision. So again, creates a hash based on that 5 tuple. Got 4 options to send it to, picks one, and so on until we get to the destination. Now what's important to realize, and a couple of people mentioned this in talks before, is that this is done on every TCP flow. So if you had a different TCP connection from these same two hosts, it would take a different path. So what happens is when you run Traceroute normally, you discover 1 or maybe 3 of the paths that are possible, because Traceroute doesn't actually send that many requests. It picks a source port if you're doing a UDP or TCP traceroute, which means you don't get to discover all of the possible paths, you discover a small number of them, which when you're trying to debug a problem isn't great because you don't know where that problem could be, you could miss it. So one of the first things that we built when we started, I never started to get bigger, was FB Traceroute or FB TraceRT, allowing us to try and figure out all of the paths through the network. So hands up who's been asked how Traceroute works at an interview. So, most of us have had to deal with this before. Well, we'll walk you through how FB Traceroute, it works just like regular Traceroute. The thing is, it just sends a lot more packets from a lot more source ports. So, in this example, we're sending 4 packets, set the TTL of 1, send them out on the network. The first network device goes, okay, I can't deliver these packets, the TTL is 1, I'm going to decrement to 0, it's no good, send a response back. Then, the hashing occurs. So, the packets go different ways. They end up talking to 2 different routers depending on their source ports. Again, those routers respond and say, I can't deliver this. And this continues until we get to the end. But by using this tool, we can enumerate all of the paths that exist between source and destination. We can get to see all of the paths that are potentially in play between two servers. So actually, We've recently open sourced this so that anyone can go and play with this. It is a very useful tool in a small to even massive network to try and understand. When you're doing Traceroute really lies. It tells you some of the paths are available. FB Traceroute, provided you use a big enough source port range, will tell you all of the paths that potentially exist in your data center network between a source and destination. We also have a very different backbone network. And this is how we connect our different data centers and POPs together. So this is a pure MPLS network at its core. So everything is label switched in the middle. Inside our data centers, we have data center routers. This is where we go from IP to MPLS and then back again on the other side. We use this for two key features. One is auto bandwidth. We also use ECMP over MPLS tunnels, once again, to try and get as best utilization we can over all of our links. So when it comes to detecting packet loss, like everybody else, we did the standard things to start with. Once again, good old SNMP, the protocol we all love to hate, gives us lots of information about counters on the device. What we discovered pretty quickly when we started dealing with the vendors, and as we start going into the leading edge of stuff, is that those counters don't tell you everything. Sooner or later you end up looking at the non-standard counters. You get everything from SNMP, you find out there's some failure cases that aren't reported in those counters, and you end up logging into boxes and doing show platform Trident counters, getting a bunch of information, screen scraping it back. Ultimately, it's too slow often and unreliable. And this brings me to another SRE principle, which I think is really important. We do this really well with servers, but not with network devices. All of these mechanics, all the ways that you monitor a network device, is asking the network device, is it okay? And assuming it's going to give you a good answer. But what if it's broken? Like, you didn't build this stuff, you don't own this stuff, you didn't write the software. And even if you did, you should probably trust it less, because you know exactly how bad it is. So in our case, when we run our own network software, we still don't want to trust it, because once again, the hardware could be broken. There could be any number of reasons why it's reporting back. To me, it's like, you go out with your friend, you get really, really drunk, you ask him at 3 a.m., is he okay? He's going to tell you he's okay. He thinks he's awesome. Then he's going to vomit on your shoes, and then he'll still tell you he's okay, because he doesn't know he's not okay, and therefore never trust any piece of hardware to tell you that it's okay. So based on that principle, we decided, well, the only way we can figure out if a network device is working is to send traffic through it and measure it, like understand that it's actually doing the job we want it to do. Again, in servers, we do this particularly behind load balancers. You do a good layer 7 health check. You understand that that server can actually process traffic for you, so you send it traffic. So we wanted to take the same idea towards the network. So we built NetNorad. And basically it's about pinging, like sending traffic through the network, measuring where it lands. So we have a bunch of pingers, a relatively small number of pingers given the size of our fleet, and we have agents or responders that end up on our servers. Ideally, we kind of have a 1 to 100 ratio of pingers to responders. We collect packet loss and round trip time information, and we analyze and report it. So NetNorad went through a pretty considerable evolution. When we first started out, we were just running ping from Python. Like, even though we're a big company, you start simple and you build on it. You get some data, then you make it better. So once again, that didn't scale very well. We started using raw sockets and sending fast TCP probes. Again, actually, that worked really well, except for the fact that, as somebody mentioned earlier today, TCP resets, a lot of service owners use them to see if there's a problem. When you start generating them as part of your monitoring, people start to freak out, then they complain, and you say, okay, well, we'll compromise, we'll go back to ICMP. ICMP has another problem. ICMP doesn't have port numbers, therefore it doesn't hash well, therefore you don't get to see all the paths. You have the ECMP problem. So now, finally, we've settled on UDP probing with a responder agent. Now, I like and dislike UDP probing. I like it in the fact that it's very similar to TCP and you get the same port numbers, you get the same hashing. It behaves in mostly the same way. The thing I dislike about UDP probing is that most of the traffic in your network is not UDP, it's TCP. Now, fortunately, because of the issues we've had with TCP probes, we've really had to compromise on using UDP. Ideally, I'd actually prefer to use TCP. So how this all works is, pingers have a list of targets they're going to send pings to. Responders simply basically just echo that reply back. It's just a simple UDP ping packet. Every see, people record timestamps. We timestamp we send the packet. We timestamp we receive it. We also put a timestamp in it from the responder so we can figure out what the latency, if the latency is the same in each direction. We have a very high ping rate, so the pinger is really, really fast. We can do up to 1 million packets per second from a single host. The responders, because they're very distributed, we're basically trying to run them on the vast majority of machines that are in Facebook. They have a pretty low load because they're dealing with a much smaller amount of traffic. The other problem is, a few years ago we said, you know, QoS is awesome, we should start using it, but you don't have one network when you run QoS, you have several networks because you need to test all the different classes of service. So we said, well, instead of just testing the network once, we need to test the network multiple times with different types of probes, with different types of service to understand that everything's behaving. We've also open sourced this, so the UDP pinger is something you can download and play with in order to actually generate traffic in your network and see what it does. So UDP probing, why UDP? Well, once again, No TCP reset packets, people got upset about that. We get efficient ECMP, and most importantly, it's extensible. We can put whatever we want in the response. One of the things we decided, or we thought about doing, and I don't think we've implemented yet, was, well, if the server's under high load, we probably don't want to trust the data it gives back. What if we put some load information in the response, so then the pinger can go, oh yeah, like you responded pretty slowly, but you're really busy right now, like maybe I'm going to take your data a little bit less seriously than a lightly loaded host. But that's, again, we can build all of this stuff into this because it's just simple UDP packets. So how do we process this data? Obviously, it's a lot of data. We have potentially tens of thousands, if not hundreds of thousands of targets. We have hundreds of pingers. It's a lot of data to process. And ultimately, we don't care about the individual host. We don't care about the individual responders. We care about the rack that they're in or the cluster that they're in. We care about bigger units of capacity than the individual host. We don't care if the host is down. We don't own the host. We own the network devices. So to move on, we need to talk about our network hierarchy a little bit. So we have this backbone, which is in the middle, which is basically everything's connected to. So connected to the backbone, we have a region. A region is basically a physical location where we're going to put data centers. We're actually building a new one in Clonee right now, so we're actually pretty excited that we're going to have an entire region in Dublin, the second one in Europe. Inside a region, we have multiple data centers. Inside a data center, we have multiple clusters. A cluster is basically just a unit of capacity that's a bunch of racks. So inside a cluster, there's a bunch of racks. Obviously, we have multiple regions connected to the backbone. We also have POPs, which are clusters. Basically, they're effectively, from our network topology, look like mini data centers. So they have clusters in them as well. So the first thing we do is we ping inside the clusters. So this is an example. We have rack switches on the bottom. We have cluster switches at the top, which is basically the aggregation layer in our network. We have a bunch of pingers, well, a couple of pingers, and we have responders. So we basically try and ping everything inside the cluster to give us a real complete mesh of what's going on in that cluster. And therefore, we can see everything. This is where we get real granularity down to we can understand that every rack is performing or not performing in our network. We store time series by host and by rack. Slag's real time are 2 to 3 minutes. Ultimately, that's actually how long the ingestion on our monitoring system or our metric system. We put metrics in, we can't read them back 2 to 3 minutes. That's basically how long it takes for us to understand what's going on. But also, we ping the cluster remotely. So we do this ping inside the cluster to make sure the cluster is healthy. We also want to make sure that the rest of the network is healthy as well. So here, for example, we have a target cluster in one of our data centers. From another cluster in the same data center, we send pings into that target cluster. We also do the same, so we have another data center in the same region. We send requests from a pinger in that other data center to this target cluster. And then we have a different region, so a completely different part of the world. We send traffic over the WAN to this target cluster. So therefore, we have same data center, same region, and outside of region. Then we alarm on packet loss. So we build time series based on this loss. We put in some percentiles, so we track percentiles, usually the 90th percentile or 99th percentile, depending on how aggressive we want to be on our alarming. And then we have thresholds. So we have a threshold for going into alarm and a separate threshold for going out of alarm. So when things start to get bad, we wait for things to get reasonably bad. And by reasonably bad means we think customers would notice. We go into alarm. We make sure that we have things very much under control before we come out of alarm again. Time to detect is about 20 seconds. So we have the 2 to 3 minutes for our metric system to deal with this. Once this data comes out the other side, we can alarm effectively inside 20 seconds, say, we have a problem. We can't talk between these hosts. So isolating, so detecting these problems is great. But once again, you've said some hosts can't talk to other hosts. How do we actually know even what part of the network to look in, especially if we're doing from one region to another? So with NetNorad, we can do some reasonably coarse isolation. Like if we have a cluster, Pinger 1 says, I see no losses, cluster, everything looks good. Pinger 2 in a different data center says, hey, wait a minute, I see some loss. Pinger 3 in a different region says, hey, I see some loss too. Well, actually, like based on that information, we know, well, inside the data center, the network's probably okay. But outside the data center, there's probably an issue, and that means it's likely the spine switches, which is where data comes into the data center. So this worked really well for a couple of years. Then, of course, we want to bring up another SRE principle. Scaling always makes things just a little bit more complicated. The solution that worked a year ago doesn't necessarily continue to work as you get bigger and bigger. And what happened was we started building our fabric networks bigger and denser. And therefore, when we have something like this, it's like, well, in between two servers right now, in between two servers, two different data centers, there's potentially, and realistically, there's over 1,000 paths, over 1,000 individual links between two servers in two different data centers in the same site. So in Clonee, we will have servers where there's literally 1,000 different options that you can take, 1,000 different individual links that your packet could touch going from one to the other. So while we can alarm, we need another SRE principle in here. Our alarming should be as accurate as possible, and we need to have a clear path towards auto-remediation. Alarming is great, you're still waking people up, you're still paging people. We need to have a way of finding out where these problems are, down to a much more granular level than there's a problem with the spine switches. There's lots of spine switches now on the edge of a data center. That doesn't narrow it down enough. So to explain what we did, is we started a new project at the end of last year called NFI, or Network Fault Isolation, or essentially to answer the question that we have no fucking idea what's going on in the network if something's broken. So basically what this is a, once again, very simplified version of our network, because actually it's a lot more links, but you can only draw so many links on a PowerPoint slide before you get really bored. So explain, so we have a host on the left, we have a host on the right. Data center 1, data center 2. So host is connected to a rack switch. Rack is connected to what we usually call a cluster switch. Cluster switches are connected to spine switches. We have inter-data center switches in the middle, with 6 of them. Then on the other data center, once again, we have spine switches, cluster switches, rack switch, and a host. So what we want to be able to do with this system is find out what if there's a bad fabric card somewhere right in the middle of this network. We'll get a bunch of NetNorad alarms saying data center 1 can't talk to data center 2, but that doesn't narrow it down. Like even here, we've got lots of devices. In reality, it's a much larger number than this. So like, how do we figure out this has gone wrong? And even worse, what if there's a bad link, once again, right in the middle of this topology? How do we actually find out where it is? And you might say, well, why do you care? Like you've got so much aggregate bandwidth in here, the amount of packets that are going to hit this is going to be really small. But what's important to understand is that all of the hashing is done on TCP level, not on packet level. So what happens is, and what's really hard for people to debug is, let's imagine we have a MySQL database on host 1 that's doing replication to another database on host 2. Let's say there's 2 databases that are replicating. They're doing replication on 2 separate TCP streams. One of the replications works fine, one of them is slow because it's dropping every 100th packet. It's really hard to debug for an engineer to go like, these things are all working. You can tell a network engineer, like, there's something wrong with this network. Like, he does a bunch of trace routes, he does a bunch of pings, everything's fine, because unless he says a TCP flow and he happens to choose the right source port to hash over this bad link, he's going to have no ID. He's not going to have any way to isolate this. So what we decided to do is, well, what network engineers do is they use Traceroute to find this. So like, what if we scale up Traceroute and just do it all the time? So that's what we did. Once again, we took the idea of hashing. We said, well, let's just send a ton of Traceroute requests from a sample host that we have to another host in another data center, and let's do it in reverse. So what this gives us is we can map the entire network. So we basically send Traceroute requests, TCP Traceroute requests, from literally thousands of different source ports. So from one host to another in different data centers, we basically build a map of the entire topology by sending lots of TCP Traceroutes. And then what we do is, well, then we start sending lots of Thrift requests in both directions. So Thrift requests are Facebook basically internal TCP requests. They're a way of sharing data. We effectively just use them as the same way we use the UDP pings. The reason I like Thrift requests is I like TCP because pretty much all the internal traffic inside of Facebook is Thrift requests. I like our test traffic to look just like real traffic. And how this works is, okay, we're sending all these Thrift requests. So we do the trace routes every couple of minutes to kind of rediscover the topologies we understand. When we send these Thrift requests, we send them from specific source port numbers. So instead of just saying, I'm going to send a request to this destination, we say, I'm going to send a request to this destination, but for every request, I'm going to pick a source port myself. So therefore, we take this same range of thousands of source port numbers and start sending requests basically as fast as we can. So literally hundreds, if not thousands of requests per second from client to server. But what the interesting thing is, when we start to experience loss, when we drop some of those Thrift requests, we know, given that we've done TCP trace routes with the same source port and destination port to the same source IP and destination IP, we understand where those packets should have touched. So therefore, we can map that loss in the network. So therefore, if I drop a single packet, I know, well, if I send it from this source port to this destination, these are the paths it would have touched in the network. If I drop another one, I can map that on the network as well. Therefore, every minute, we look at all the data of all the packets we dropped, we map them onto the network, and we say, okay, if we overlay these onto each other, this should give us a pretty clear picture of the link that is dropping all the traffic. So very naively, I said, well, basically what you do is you, as increment, every time you see one of these links, you create a counter for it. So you map the entire network, set everything to 0, start sending these packets across, you drop some packets, you map them onto these links, and lo and behold, the link with the highest score is the one that's dropping packets. But in this example, you actually get 2 links that are possible. And there's not really clear which one's broken, because once again, we've overlapped twice on the first link, and we've overlapped twice on this link in the middle. So I scratched my head at this for a while and said, thought this would be much easier than it's turning out to be. But then I thought about the network topology for a minute, and I said, like, I've totally missed something here. And it's all about statistics and statistical likelihood of something happening. When I looked at this a little more deeply, I said, well, wait a minute. That link on the left, he's 1 of 4. Therefore, you've got a 1 in 4 chance of hitting him every time you send a request. That link in the middle that got hit twice, there's a 1 in 48 chance of hitting him twice each time. Therefore, it's statistically much less likely to hit that link twice than it is the first one. So we need to factor that in. And there's another thing we can factor in as well. So it's not just how statistically likely we are. Of the requests that I dropped, what percentage of those requests happen to hit this link? So in this case, 100% of the requests. So if I'd lost another one which took a completely different path, that one's still the highest probability of failure because it's seen 2 of it and 2/3 of the loss have been on that individual link. So when we put this into the map, basically what we did was we took the size of the network and basically factoring the statistical likelihood of one of these links being bad, but taking the same data, doing some very simple math of basically saying, well, like this link has been hit twice, but it has a 1 in 48 chance of being hit each time, then suddenly that link stands out really clearly. This is probabilistically the most likely suspect in our network, right in the middle where something is broken. And that's all great. This all looks like a wonderful science project at this point. I came into work one day, I think it was January, was it? Yeah, January 9th or January 10th, I came into work, and I saw this graph, and I was like, this is interesting. This is the first time. We'd only been running it, like it had been basically a prototype up until this point. And I went and I turned to Jose, who's the network engineer behind me, and said, like, there's something up with this device, like it's clearly standing out here. And he's like, I don't know, I'll have a look. And he logged into the device, looked at all the counters, looked at all the graphs, everything looks fine. He said, well, no, it looks fine. And I'm like, this looks pretty broken in here. I know, like, I just built this shit and I don't trust it either, but like it's clearly different to everything else. And the whole point of this is to find outliers, is to find the thing that's behaving much differently to everything else. So the first drop was like, he said, fine, I'll just drain it and see what happens. So he drained it and suddenly all the loss went away. So like, this is deeply suspect. And then I said, well, I actually have a new version of the code where I've changed the math a little on how we cut. So I was like, let me push that version out and see what it does. So we pushed it out, and then we turned the device back on again, and the loss came back, and we turned it off, and we turned it on, and we're like, yeah, okay, I'm pretty sure there's something wrong with this device. So we went back to the vendor and said, like, what the hell's going on here? And they said, oh yeah, so there's this hidden counter in here that you have to run like these millions of shell commands to get to, but like you can get this data out. And we're like, that's great. And they're like, oh yeah, but there's like 1 million of this counters inside this ASIC. And we're like, yeah, okay, you need to aggregate that for us because like we can't probe that all the time. But the really nice part is like the vendor at this point wasn't exposing this. The vendor up until this point, we're pretty sure, didn't know this was a way that this device could drop packets. But we managed to discover a device literally in the middle of our network that was dropping, it was only, a small percentage of packets, but it was something that stood out as a statistical anomaly in this data. So we rolled all this stuff out. We're like, okay, this is pretty cool. We still have some issues, right? Firstly, the latency data we were producing, so most of the lost data was actually generating all these graphs and giving us good data. The latency data wasn't great, and latency is actually really important in network monitoring because latency data shows you buffering in network devices, which is something that I only learned after building the first system like this in a previous job. It's like, okay, loss is great, but like most network devices will buffer packets for a while before they start dropping it. And therefore you can see when your network is congested, and especially with microbursts, so you see like these bits of little congestion or very small amounts of congestion, you'll see it in latency before you actually start dropping packets. So therefore, it's actually really important to measure latency really, really well in these kinds of systems. Also, the request rate was too low. Obviously, the more requests we can get, the more samples we get, the better we can triangulate. And we weren't doing this very quickly. We had coverage issues, so we weren't covering the entire network. We basically needed to have hosts in each cluster to be able to cover all of the links in and out of that cluster. And we were only covering the data center. We hadn't figured out, and admittedly, we still haven't figured out what we do in the backbone. So the first thing we did was like, let's restructure the code a little bit. So originally, it was kind of a monolithic client and server. All of it was written in Python. We kind of broke up the client and said, well, there's actually two core components to this. There's the thing that sends thrift requests and this thing that does trace routes. The thing that does trace routes, it was originally we were just calling traceroute. We actually had this binary inside. It's actually the same thing that FB Traceroute is built on called ztrace. It does very efficient, large-scale trace routes. We said, well, let's start using that first. That'll make it go a bit faster. And everything else. We said, well, how do we make this go faster? And then we said, well, you want something to go faster, Python's probably not the right answer. So we decided, well, let's write the server in C++ because C++ was chosen for a couple of reasons. A, I wanted it to be fast. B, I really fucking hate Java. Like, you have no idea. And lastly, I hadn't written C++ since I was in college, which sadly was a long time ago, but I thought, after 10 years of Amazon, I think I proved that I kind of enjoy pain. So I thought, well, right, I'm going to write this in C++. And also, once again, C++ is very well supported. Like the actual Thrift underlying libraries are all written in C++, so it's like, well, it's the obvious thing to use. And then said, well, if we write the server in C++, we should write the client in C++ as well. And it turns out, hard to believe, C++ is actually a lot faster than Python. And I mean a lot faster. So this is the latency data we were getting. So you probably can't see, but it's like 6 or 7 milliseconds to do these very small Thrift requests when we were doing the Python server. We rolled out the C++ server, and suddenly we went down to 1 millisecond. And much more importantly, there's almost no variance in the stack graph. So it was like, okay, now we have clean data. And I was like, well, let's change the client as well. So this is when we rolled out the client. We also doubled the request rate when we rolled out the client. And again, once again, the latency falls way down, and again has less variance overall. So once you're like, okay, we have clean data and we can go way faster, we can generate more stuff. Then the next problem was Traceroute is a unidirectional system. You do a traceroute to something, you get responses for everything, all of the hops from client to destination. The path back, you don't understand. And it's not going to be the same as the path you got there, because every router in the reverse direction is going to make a different hashing decision based on that packet. So we're like, okay, well, we knew this right at the start, and we're like, well, okay, half our data is actually going to be bullshit, because we don't know the reverse paths. So therefore, we're signing all the loss on all the outgoing paths, not on the reverse paths. So we said, well, this is kind of, it was acceptable, and it actually gave us good data, but then we ended up having to make sure that every client was hitting every server to make sure we got full coverage from both sides. So we said, well, what if we did reverse trace routes? So what if the server, when it started getting requests from somebody, said, hey, the client can actually tell the server, like, do some reverse trace routes to me on the same port range that I'm sending requests to you to. Now we can understand the reverse path. So the client, once he starts up, he starts sending the normal Thrift request. He also sends a special Thrift request that says, hey, start doing reverse trace routes. And then every couple of minutes, he goes, give me all your traceroute data back to me. Now what we get is, we can build a complete map of both the outgoing path and the incoming path. So therefore, for every Thrift request we send, we know all the links it touched on the way to get to the server, and all the links it should have touched on the way back. So again, this means we can do, it makes our data twice as good. We can do half as many requests and get twice as much value out of them. Also, well, what's next? So the other thing, in terms of coverage, is a problem. So I was like, well, we have these switches called wedges, which we build ourselves, and they're really just Linux servers. And my code is now just a little, the server code is just a little C++ binary. Wouldn't it be awesome if I could just put it on the switches, and therefore I don't have to worry about servers, I don't have to worry about getting servers all over the network. I can suddenly run this thing basically on the edge of the network everywhere. I haven't figured out how to do that yet, but I'm hopefully going to do it soon. The other big thing is the backbone, right? The backbone is MPLS. Traceroute doesn't work so well in MPLS land. Sometimes it does, sometimes it doesn't, depending on the vendor. More importantly, LSPs change all the goddamn time, as in multiple times a minute. One of the things is the data center network is quite stable, so we do traceroutes every few minutes. We get to build that topology, and that topology stays pretty stable unless there's actually something physically changed to the network. Here in MPLS, that's not the case, so we haven't actually figured out how exactly we can do the same kind of thing, and that's why we kind of compartmentalize the software. We've had this traceroute part of it will eventually become a, hopefully figure out what the hell MPLS is doing part at any given point in time. But this takes us to the SRE principle. Engineer time is our most valuable asset. And this is the thing that, this is a great kind of project, I think, for SREs in general, because SREs have 3 very distinct skill sets. And it's quite rare to find good SREs. Just give me a moment here. This is important. It's all tied together, you'll see. It's all about preparation. So, the first thing is a good SRE has a good knowledge of systems. Not only how systems behave, but how systems scale. High quality ingredients, very important. So we'll call this the systems part of this solution. So again, by itself, nice, not necessarily wonderful. I don't like drinking straight vodka. Pineapple juice, freshly squeezed pineapple juice, of course, not from concentrate. Also very important. We'll call this a networking component. A little softer, a little sweeter, perhaps. And the last, and ultimately the most important and beautiful part of an SRE skill set is the coding, which we shall represent today by Chambord, a wonderful blackberry liqueur. So, when you combine all these things together, you can build something or make something that's much better than the sum of its parts, which to me is exactly what an SRE does. They're not really an expert at absolutely everything, but if they can combine those disparate skills together, they can build something that's really cool. And also, to me, You don't want to waste time debugging problems when there's much more important things to do. And I'm sure the recruiting people would like me to say that, you know, we're hiring and all that bullshit. What is much more important is that we have a fully stocked cocktail bar in the Dublin office. And we use it quite regularly. And actually the best part is we expense all the booze under office supplies, which I think is the best way to do it. So thank you very much. We'll do 5 minutes for questions and we'll let Adam go. So any questions? About cocktails, networking, whatever.
What's the name of the cocktail?
It's a French martini, actually.
Is it good?
It is quite good. Yes, we've done quite a bit of experimentation in the office. It's not all networking in the networking office, it must be said. Yes?
The NFI part, is it real Traceroute with TTL exceeded coming back?
Yes.
And how much load that must schedule it onto what's the acceptable overhead?
That is the interesting part, right? You can only trace routes so aggressively before your routers go like, hey, I'm not sending you any more ICM TTL expires. So that is actually, that's the reason why we have Traceroute and the request on compute separately, is that realistically, we do the Traceroutes as aggressively as we can. We do actually monitor the counters for when they start hitting cop limits on the network devices, and that's kind of when we dial it down a bit. But that is really the limiting factors. You can't traceroute the network constantly. We basically do it at a 5-minute interval, and we try and set the request rate so that we don't overload it. But yeah, that's a limiting factor in how quickly we can map the network, is how fast you can actually get routers to respond to ICMP TTL exceeded. Okay, your show, Adam.
I thought you were leaving. Oh, he's doing it. Oh, there we go.
What kind of guy would I be?
Thank you, Richard.